Hello, this is my lab report, and my name is Ari. So the purpose of this lab is to explore Faraday's law by collecting data about the magnetic flux, field, and then the induced flux and current. And so for the preview of this lab, I found that my experimental time when calculating these was 1.2 seconds, whereas the coded time for the simulation was about 0.67 seconds. And so in order to compute this lab, we first need to understand a few things about uh, magnetic flux and force. So here we have the Biot-Savart law, which is basically detailing about the magnetic field in a long wire, which we are simulating. Flux is shown right below that, which is the one with the integral B dot NDA, and then Faraday's law, of course, which is the last one of the EMF, in order to calculate the induced flux and then the electric field. And then, of course, we have Ohm's law, which is V equals IR, and Newton's law, which will help us calculate the force of gravity and relate it to the force of the magnetic field while it's in the tube. So in order to do this lab, we first have to make some assumptions. We have to assume that air resistance is negligible, which just simplifies our force calculations. This is also related to the second part, which is that magnetic force and gravity are the only force acting on the system, just so that we can make them equal to each other and then solve. And then the bar acts as a magnetic dipole in order to simplify these calculations using the Biot-Savart law as shown before. So the system was that it was the magnetic bar and then the aluminum tube. The surroundings were everything else in the room, and then the initial conditions are shown here, which are just the dimensions of the aluminum tube. And basically, the setup was just dropping the magnet through the tube and timing how long it took. So as we can see here, we would drop the magnet down the aluminum tube and then record time and then repeat for 5 trials. You can see here that the average time of these 5 trials was about 1.2 seconds. And then after that, we had to code a simulation. So you can see here at the beginning some constants of just like the graph of the gravity, setting up the graph, all of the constants of the dimensions of the tube, and then the first part here that you can see on the right is just setting up the actual simulation for the tube, and then calculating and simulating a bar magnet. And then on this part, it's kind of cut off, but the top part is just calculating the magnetic dipole, which we've done multiple times. And then the second part is creating a function in order to calculate flux throughout the tube. And then these slides are the last two slides of just calculating the time in the tube, as well as calculating the magnetic force on the magnet down here at the bottom, and then coloring each ring according to the current within the simulation, and then setting the magnetic force equal to the magnetic force on the magnet and the magnetic force on the ring, just summing them up, and then we then apply Newton's second law to calculate the velocity to make the graph, as well as set F net equal to F gravity plus F the magnet in order to make sure that they're equal to each other. So then the results of this code that you can see is that here we have the simulation on the left, the red and the blue, and then we have the velocity time graph, as well as the results that the simulation took about 0.67 seconds to get through the tube. And so the results of this graph, actually what this means is that the force of gravity is greater than the magnetic force as the magnetic enters and leaves the tube, which you can see right here at the beginning and the end of the graph, because since the velocity isn't constant, that obviously means that the bar is experiencing a net force, which means that the gravity is greater than magnetic force. But here in the middle, while it's inside of the tube, magnetic force is equal to the force of gravity on the tube. So for the discussion questions, which color corresponds to which current? Red is counterclockwise, blue is clockwise. We can tell this by Lenz's law. And then what happens when you flip the magnet around? Basically, it falls in the same amount of time, but the direction of the current flips because you flip the direction of mu. How does the total time in tube compare to that of the computational system? So it was similar, although the computational time was much shorter by about half. And this is because of the assumptions we made, so that adding more rings to better simulate the tube, and then accounting for air resistance would then make it more accurate because then, of course, magnetic and gravitational force wouldn't be equal. And then what does the shape tell you about the graph show you? So it basically says what I said before, that the gravitational force is greater than the magnetic force when the bar is entering and exiting the tube, but they're equal inside of the tube, which is why the graph showed a constant line for velocity. So some errors that could have been present in this lab was that human error with a stopwatch would have skewed results in inaccurate timing, like I might have timed it too late or too soon. And then, of course, not accounting for air resistance just skews the force calculations because, of course, that means that magnetic isn't exactly equal to gravity, but we had discounted this for simplicity's sake. And so for the discussion questions, what if the resistivity of the conductor were reduced as close as possible to zero? By Ohm's law, which we had shown before, less resistance means induced current, means more current, so the magnet would actually fall slower as it is repelled. And then what if holes or slot were cut into the tube? So this means that there would be less rings, so that way the magnetic force decreases, and then with less of magnetic force counteracting gravity, the bar would fall faster. So kind of the exact opposite of what would happen if you decrease the resistivity. Thank you for your time.